everyone, welcome back to Radiosity, and this is part 2. Okay, cool. So just a quick recap, we want to really color a scene, right, which is composed of some region X, and that region has some objects, right, so we want to color some V in X, right. Also I should mention that I didn't mention in the last video that X has some boundary, right? Let's call that dx, because we want to have the ability to color a scene with specific boundaries. Because it's really hard to say we want to color a scene that does not extend; it just exists, if you know what I mean. And to do that, we want to calculate the intensity of photons at each point in X. And I guess the idea here is if we think about the RGB coloring again, so we do have the RGB. If we calculate the intensity of photons that are red, green, and blue, and we can put them together, then we have an intensity function for RG and blue, right? And then that way we can color the entire scene. So that's going to be our, I guess, task. Okay, cool. So a quick recap of density, first of all. So density. Okay, cool. Let's suppose we have some metal rod. And at some point X, what is the volume? What is the volume of that rod? Well, I guess at a point it doesn't really make sense, right? What is the volume at a point? It's 0, right? So let's instead consider some interval around X. So this is some dx. Okay, cool. So that's our little interval. The way we would do that is, well, if we do have our density function, and let's say the density at point X is delta X, then that's going to be our volume, right? But what if we want to integrate over some kind of, what if we want to find the volume over some interval, right? Well, it's very similar. So we do just take the integral over that interval of delta X dx. And I guess that's just a recap of density, and it's going to be useful later on because we are trying to calculate the density of photons at a particular point. Okay, cool. So I'm going to define some couple other things right here. So photon counts and phase spaces. So okay. So our phase space is the space that we're going to be working in, what the scene is going to contain, right? And from the last video, if you remember, V is a set of all positions that we were going to be looking at, and the viewer only looks in a certain direction, right? So we want to capture that particular direction. So that's why our phase space is just going to be V cross omega. Omega is going to be the set of all directions. Okay, that makes sense. Now, density, right, in this case, if I draw some kind of random looking scene, right, for some x, for some point x, we want to calculate the density of that at that point, the density of photons in specific. And I guess the way we do that is count the number of photons and divide by the area, right? And we also, so that's basically what density is. So the way we can maybe define a function called n. I'm going to try to keep these vectors because the positions are vectors really. X omega, so in a certain direction and at time t, because photons do move, right? And in 2D, I guess the units are, well, think about it, right? Density is the number of photons over meters squared, because in 2D we just have like the area, and then radians in a particular direction. So then in 3D, similarly, we do have the number of photons per meter cubed, and this is going to be important per steroradian. And steroradians, if you guys remember, are from 0 to 4 pi. So 0 less than NESDD is going to be less than 4 pi. Okay, cool. So then what about the number of photons in the entire phase space, right? What about in V cross omega? Well, I'm going to define that similarly, except I'm just going to use a big N of V omega, and at some time t, And that's just going to be, well, we integrate over our phase space. So we take the integral over v, the integral over omega, and we do have our little function. So density at a particular point. So at n of little x, omega, and t, and this is going to be all dx, actually d omega dx. And the way what we really want to be finding is something like the phase space flux, right? So if you guys remember, we want to calculate the intensity of photons at a certain point, and that way we can, like, I guess, reconcile with the RGB notation, and that will help us color the scene with, like, the lighting included. And the way we're going to do that is using phase space flux. So phase space flux. If you guys remember, in maybe physics or some kind of like calculus course, you might have defined flux to be how much of a vector field is going through another area, a region, right? So for example, how much wind is blowing through the door, how much, so basically something like that. So that's basically what flux is, and we're going to have to define that for like how much photons are going through a certain point. So that's going to calculate the intensity. And in the 2D problem, I guess, let's just define our flux. Maybe we want it to be u of x omega t. And I guess 2D, the units are going to be the number of photons per second, per meter, per radian. And similarly, in 3D, it would be number of photons per second, per meter squared, per steradian. Okay, example problem. So let's suppose that the value of u is known at all times. So let's just suppose the value u is equal to 4. Then suppose we're trying to, omega is perpendicular to some line segment. So we have omega perpendicular. And say the length of this line segment is equal to 0.01. Right? And let's just say over 1 second, and we want to say that range of 0.05 radians, because we're still working in 2D. So how do we calculate what the number of photons are going through per second, right? So we do know that 4 is equal to, well, the number of photons. So we do have 0.01, which is the length, times 0.05 times, this should be a multiply, and is equal to the number of photons. And this is just going to equal, what is it, 0.02, 0.002. Okay, so that makes sense. What if omega is not perpendicular? So if I do have some kind of omega, and it's not perpendicular to this, to this, whatever line that we're trying to calculate the flux through, how does this work? So, well, we actually have a little bit of use of projective geometry maybe, and let's just draw the normal vector, right? So we do have n, and the normal vector is just the vector perpendicular to that line segment. Okay, cool. So what's the distance? I'm actually not going to call this theta, I'm going to call this part theta. So it turns out that, I guess, the amount of the flux going through this in this direction, in a particular direction, is just going to be multiplied by cosine theta, right? And I guess if you also know the dot product rule, so we have n times the magnitude of omega cosine the theta between them, that's just going to be equal to n dot omega. So that's really neat, because we could just plug that into our equation here. So we have the number of photons is equal to 4 times 0.01 times 0.05 times n dot omega. So that's really cool. Okay, cool. Now, moving on, let's just go on to the big ideas now. So let's talk about conservation of photons. So some rules, right? So we really stated in the last time, our assumption is that the number of photons going into the phase space and the number of photons going out of the phase space is going to be the same, or the difference is going to be 0. So really we want to know that, we know that d dt of the number of photons in total, so v omega t is going to equal 0. So if we do find some kind of expression for this, in terms of all our lighting, in terms of all of the givens, then that's going to be important, because then we can just set them all equal to 0 and see what comes up from there. So let's think about what might affect the rate of photons in our phase space. Let's think about it. So one might be emission. So emission. And what I mean by that is photons being generated. So if we know the light source, exists some kind of light source in the scene, then, well, photons are generated by these light sources, and there we go. We have more photons being generated by some light. Okay, number 2 is going to be absorption. And again, absorption is going to be part of the scene, so it's going to be determined by some material properties. Maybe there's water in the scene, or maybe there's smoke in the air, and that's going to, maybe the photons get absorbed by the material in the scene, and that's going to be all determined beforehand. Okay, cool. Next might be streaming, right? So what I mean by streaming is photons leaving, photons cross the boundary of our phase space. So photons cross, and boundary is just going to be dB del, and but in direction omega. And that's important because we can't have, if photons leave the phase space like v in not in direction of the omega, then it doesn't really matter to us because we won't be actually like including them. We're not going to like look at them anyway. It's not going to be part of our scene. So that makes sense, right? Photons cross the boundary, but not in the direction that we're looking in. And finally, we have photon scattering. And scattering is a bit trickier because, I mean, if we do have some smoke, say in the scene, so I'm just going to draw some like smokiness, then photons that go into the smoke, they might scatter in maybe random directions. So that's going to be a bit tricky, right? I guess like one thing to note is photon-photon interactions. Will be ignored because they do constitute very little of our entire scene, right? Finally, okay, let's just start maybe with emission, right? So we did assume photons can't be hitting each other, and under those assumptions, I guess this expression can just be calculated by adding all these up. When I say adding, it could be subtracting also, because plus emission minus absorption, because when photons get absorbed, they're no longer in the scene, minus streaming, and then plus or minus scattering, depending on whether they scatter outside their phase space. Okay, let's keep moving, right? So let's maybe go on to emission first. So say we do have, because emission is completely dependent on the scene, right? If there's a lot of light sources, then a lot of photons are going to be emitted, right? And they're going to be produced. So I guess for rendering, emission only happens because of that one idea. So suppose emission in the scene is going to be defined by Q, X, omega, T. So at some particular point X and at some particular direction omega, and at some time T, there's a number of photons being emitted. Then I guess in the entire scene in our phase space, we want this total number is just going to be the integral over V integral over omega of Q, X, omega, T. And this is going to be d omega and then dx. Cool. So that's emission. What about absorption? So keep that thought in your mind. I'll erase this and be back.